This lecture is meant to introduce to you one of the most fantastic theorem in calculus, which is known as fundamental theorem of calculus. As I have mentioned at the end of my previous video, that up till now, while we worked with developing the theory of Riemann integrals or definite integrals, we have not used any results related to differential calculus. But here we are going to establish a fantastic relationship between integral calculus and differential calculus. I thought of making this lecture in a like you would see in a traditional classroom, so that you get a good feeling of the result, or at least the statement of the fundamental theorem of calculus and some applications, and we will go back to the to our original method like slides from next lecture onwards. So let's see what does fundamental theorem of calculus says. So fundamental theorem of calculus. So we will often refer to it as FTC in our future lectures, and here goes the statement. So what we need a function which is Riemann integrable on a closed and bounded interval. So suppose that if from the closed interval AB to R be an integrable function. We know what are integrable functions. We have discussed the definition and properties in great detail. So from if I am going to define a function, define big F from AB to R by fx equal to integral a to x ft dt, where x belongs to AB. So you may be wondering, okay, we know that f is integrable function on this closed interval AB. Does it mean that f is also integrable in this closed interval AX? But we will come to this in a moment. But let us first see what the fundamental theorem of calculus says. So it says that the function if is continuous. Not only that, it gives us a rather strong statement. In fact, if satisfies what is known as a Lipschitz condition. Namely, there exists an alpha in R, let's say in general alpha is bigger than or equal to 0, such that for C in AB we always have fx minus fc is less than or equal to alpha times x minus c. You may easily see that even if I give you this Lipschitz condition, it will mean that the function if big F is continuous. Now fundamental theorem of calculus comes in two parts. So let me call it part 1. Part 1 says that if is continuous on the closed interval AB, or let me make it a little less general, continuous at a point C in AB, then big F is differentiable differentiable at the point C. But when I say that a function f is differentiable, you will ask what is the derivative of f at C. Here we allude to our intuitions, and it turns out to be correct that peak f prime C is equal to f of C. This is the first part of the fundamental theorem of calculus. Part 2, it says that if small f is differentiable and f prime, the derivative of f is integrable in the closed interval ab, then integral a b f prime t dt is equal to, yes, as exactly you might have guessed, fp minus f of a. We have seen this kind of things in our high school mathematics. So now, as I have mentioned before, I have to make sense of this fact that this integral is well defined. Okay, so here what we need is a fact which I have not mentioned before, but maybe I should have, but let me write it down here. So it says, so there is a result, let me call it a proposition, and what is the proposition? It is called domain additivity. So let me bring it here. Domain additivity of Riemann integrals. So what does this say? This says the following: let f from AB to R be an integrable function. Okay, so be not yet an integrable function, be a bounded function, and that C is a point in the closed interval AB. What do we have? If, okay, so let me make it a formal statement. We have f is integrable on AB if and only if f is integrable on AC and f is integrable on CB. Moreover, in such a case, we have integral AB to of fx dx is equal to integral AC fx dx plus integral c to b fx dx. Now here in the statement of fundamental theorem of calculus, this point x lies somewhere between a and b. So this is our closed interval a, and this is b, and our x lies somewhere here. So since f is integrable on the whole interval, by this proposition, domain additivity, we see that f is integrable in this interval. Also we have f is integrable on this interval, but in the statement of fundamental theorem of calculus, we do not make use of this fact. Now how do we make use of such kind of statements. So let me work out an example. So let me work out an example. Okay, so let me work out a few examples. Let's say the first, do we always know how to compute the function big F if a function small f is given? Okay, let me first give you an example for that. And here my example is of a function if from the closed interval ab to r, which is given by what you call a floor function or a box function. So you take any x and you send it to the floor function. So this is also known as the greatest integer function. Greatest integer function. So if I want to give a particular meaning to AB, we can consider this function from -1 to 1. From -1 to 1 to R. So for example, if you would like to draw the graph of this function, let's see how it looks like. So here is our y-axis, here is our x-axis, and let me try to pick another color. So when x lies in the interval -1, 0, then we know that the box function is given by -1. So for example, if x was -12, then the greatest integer less than or equal to x is equal to -1. So if this point corresponds to -1, then from here to here our function, the graph of our function looks like this. And when x lies between okay, so here strictly speaking this is an open interval, and here I should take the closed interval 0, 1, and we see that from here onwards the graph looks like this. The greatest integer function of any element inside this closed interval 0, 1 is equal to 0. So here the graph ends somewhere here, it does not go up to 0. Okay, so now can we, so first of all we see that f is not continuous, but one of the parts, or the part that really comes before part 1 of fundamental theorem of calculus, shows that the function big F, if we can construct it, then it should be continuous. So let's see. So what can we say about this function? Is this integrable? So is small f integrable? The answer is of course yes. You can use many facts that we have proved, but the easiest that comes to me that comes to my mind at this point of time, it is a monotonic increasing function. So this is a monotone function, and we have stated that monotonic functions are integrable. So this is a monotonic function and it is integrable. So by fundamental theorem of calculus, by FTC, the function big F, which is defined from -1 to x, ft dt, is continuous. If you try to work out what is the function f, so this is actually f of x. So what is f of x? You can easily compute. I am not going to give you the computation, but rather leave it as an exercise. I have done this kind of things before, so I am allowed to do so. So minus x minus x, -1 minus x, if x lies in the interval -1, 0, and -1 if x lies in the interval open 0, closed 1. So if you want to plot this graph, let me try to do it for this example, so that you get a good feeling of the same. So this is our y axis, this is our x axis, and when x lies in the interval 0 1, it is a constant function which is equal to -1 everywhere, so it would look something like this here. And when x lies between -1 to 0, it will be -1 minus x, so looks something like this. So in particular, we have used fundamental theorem of calculus on this if, not really full force of fundamental theorem of calculus. We have just constructed this if, which is a constant function, and we have come from here to here. We gave this is a continuous function, so a non-continuous function gave rise to a continuous function here. Okay, so but this function was not continuous, as I have mentioned. But let me work with another example by taking a function which is actually continuous. So example, so let me try to do another example, call it example 2. So let me take this function again, f from -1 1 to r, and this function is given by fx equal to modulus of x. We see that this function is continuous. So this function is continuous, and any continuous function is integrable. So at least we know that we could write down this function -1 to x ft dt and call it fx. This function is going to be continuous because it is the function small f is integrable. And again, let me not do all the calculation and simply write down what is going to be the function 1 minus x square by 2 if x belongs to -1 0, and 1 plus x square by 2 if x belongs to 0 1. So I am leaving all these things as exercises, but there is one catch here. So this exercises, you should not do these exercises, you should not use indefinite integrals that you have learned in your high school. You should be able to do all these computations with the theory that we have developed till now. So the function bgif that we have come up with by doing this kind of integration, as you can find in the fundamental theorem of calculus, and you can see that this function is differentiable. So fx is differentiable. Just to make sure how the graph of this function looks, how does the graph of the function look like, let me try to draw it for you as well. So x-axis, y-axis, as always, let me use another color to draw this graph. And so this is our point half on the y-axis, so we know that our graph should pass through this. When we are in this situation, this is a parabola here, and when we are in this situation, this is a parabola which is going down, and we can see that this function is very much differentiable, smooth, etc. Okay, so let me finish this video by working out a rather good example of which illustrates the power of fundamental theorem of calculus in a much bigger extent. So let me do this example. So example 3. And what does our example 3 say? So the question is, suppose f from 0 1 to r is given by f is okay, so let me write g here. So g from 0 1 to r, which is defined by g x equal to integral 0 to x dt by t to the power 6 plus 1. Okay. So our first task is to evaluate g prime half. So this is the derivative of g, and we want to compute its value at the point x equal to half. And the next part asks us to evaluate the following limit h tending to 0, 1 by h x to x plus h dt by t to the power 6 plus 1. At this point, feel free to pause this video for a while and try to work out this example. If you can on your own, I'm sure that many of you will be able to do this example, but now let me do it. So first we look at this function f of t. F of t is given by 1 by t to the power 6 plus 1. This is also defined on the interval 0 1. So no problem about that. This function is well defined, and furthermore we see that this function is integrable. Now if this function is integrable, this g, we can see that this is exactly what we have called big F in our previous video. So anyway, this question says g, let us write g is an integral which runs from 0 to x dt by t to the power 6 plus 1. So this is g of x, and our fundamental theorem of calculus, FTC part 1, this says that g prime x is equal to so it says that g prime, let's say half, is equal to f of half. This is exactly the form of fundamental theorem of calculus part 1 that we have seen. And what is the value? What was f of t? 1 by t to the power 6 plus 1. I want to emphasize that you could go on and write this in a very nice form, but even if I ask you to solve this kind of problem in your exam, you please feel free to stop right here. It is important to understand the idea rather than doing the hard computations by hand. So second part, so limit h tending to 0, 1 by h integral from x to x plus h dt by t to the power 6 plus 1. I can write it as limit h tending to 0, 1 by h integral from 0 to x plus h dt by t to the power 6 plus 1 minus integral 0 to x dt by t to the power 6 plus 1. Please convince yourself that we can write this because of the result that I have mentioned here. So domain additivity of Riemann integrable functions. So domain additivity of integrable functions gives us this. And how do we now compute it? So let me write for so this is exactly limit h tending to 0, 1 by h g of x plus h. So remember, G was given by exactly this form, minus G of x. So we know from differential calculus that this limit is exactly equal to G prime of x. What is G prime of x? By fundamental theorem of calculus, by FTC part 1, this is equal to f of x. And what is f of x? This is nothing but 1 by x to the power 6 plus 1. I hope you have now through this video understood the concept of what our fundamental theorem of calculus wants to tell us, and I have also shown you some application of this, or I have also told you how these functions are actually working. So we get back to all these things in detail along with the proofs in our next video. Thank you.